250 su target die and 9, and you should come on time. This is what I've been told. I won't be there, but someone else will proctor. Okay, and then you might want to write down when this review session is. I think when your GSI is taking care of that. Okay, and then next Monday is President's Day, so you want to have class or discussion. Now, I think that you guys have had logical effort and have had wire capacitance covered. And so I think logical effort is really important, and it's used throughout the class, so you should make sure that you understand it. And today we are going to talk about, first continue talking about wires, and then memories and decoders, okay? And so you can find where these things are in Jan's book. I think there is a whole chapter called The Wire, and that pretty much covers whatever we talk about in the wire, like today. And then there is a part on decoders at the end that is also covered in the memory chapter, which I think is this 12.3. But the slides should be sufficient, actually. All right. So first, let me go over wire capacitance a little bit again. So I think that we've seen, you should have seen that there is a substrate, right? And usually there is like some dielectric, which could be a SiO2, but it could also be something else. Okay, and then there is wires. In this, and the wires are also in some other dielectric. Okay, and so if you look at, for example, this is one wire, and this is, it's like it's got some width that you can choose. It's got some thickness that is typically a process constant that you don't have any control over, other than choosing what layer it is. And then, it's spaced. It could have a wire next to it. There could be another layer with another wire here. And then you could, imagine there's, modern processes as maybe 6 or 7 levels of metallization, maybe more, depending on what flavor it is. So you can imagine this structure repeated 9 times. Now, you can also imagine that if you have all the way a wire down here on metal 1, and there is a wire up here on metal 9, okay? The capacitance between these two will be not very large. So to first order, it's probably safe to consider capacitors that are like one layer away. But there could be cases where, not so much in digital, but maybe in analog situations where you want to really calculate very carefully this capacitance, and then you can of course do it by hand, but most likely you will do it with some kind of extraction tool. Okay. Anyway, so what are the things to remember? Okay, these are pretty simple. If you have an isolated wire, so let's just focus on this guy. If you have an isolated wire over the substrate, okay, this is connected to a substrate, and substrate is conductive, so it's really, let's say, ground. Okay. So let's say you have just an isolated wire. So there'd be like electric field lines that, go like this and like this. And so what determines the capacitance is really the distance of the wire from the substrate as well as the width of the wire. So a wider wire has more capacitance, and it has also lower resistance. Okay? And typically the product is constant. Okay? You can just make, to very first order, the product is constant. Then there is like this fringing field makes it so that it changes a little bit with the width. Okay, so this is for one wire, all right? So now if you start thinking about, this almost never happens, especially in digital, because we try to pack things very closely. And so, you always end up with one wire next to something else, okay? So imagine that now you have 2 wires. Okay, so the electric field lines will not only go towards the substrate, we will also go like this. So there will also be a capacitance, not only between this wire and ground, okay, but between this node, okay, that is connected here, and this node that is connected here, okay? And if there is a third wire, there will be another capacitance, and so on and so forth. And so obviously the closer these wires are, right, the higher this capacitance is. And then also the thicker these wires are, the higher the capacitance is, because it's just like a parallel plate to first order, right? So you should have already seen all these. And then, similarly, if you have a wire on top, then there'll be fields going like this, right? And so there will also be a capacitance to call this D, A, B. So if this is A, this will be D, and this will be B, right? So you should be able to do this. See, it's important that you can do it by hand so that you have some way to predict things. But it's also important that to know that there are tools that extract these capacitors, that your parasitic extraction tool will do it. And the reason for that is that, this geometry gets complicated very quickly, okay? So you can, the analytical equations that you can use are of limited accuracy. Typically, the accuracy isn't sufficient for verification. It is sufficient only for design, okay? So when you go into verification mode, meaning you have a design and you think that it works and you want to make sure, then you will extract, and the tools typically do a much better job at calculating these capacitors for you. Okay, and typically you can choose when you extract whether you want to get only capacitors to ground or also capacitors between different wires, right? And the trade-off there is that if you include all the capacitors, your simulation is more accurate, but there are more capacitors, which means that it's slower too, okay? So should know all this. So now I think that, so 2 questions. So to first order, we said that the wire is a capacitor, okay? But obviously, it also has some finite resistance. And usually always in microelectronics, we refer to resistance as, so you can always write, right, that the resistance is the product of the resistivity times the length divided by the cross section. Okay, this is always true, but this is not really how we refer to materials in to resistance in microelectronics, because typically the thickness, we can't choose it, and the resistivity also we can't choose it, so we can only choose the length and the width, okay? So what we do is we isolate this rho over h quantity and we call it the sheet resistance, okay? So if you open up a design manual, you won't find values of resistivity, but you will find just values of sheet resistance, okay? And the sheet resistance, as you know, is the resistance that a wire will have if its length was equal to its width, okay? And then you just multiply the sheet resistance by the L over W to get the total resistance. So if you look at the materials that are used in microelectronics, these are values of resistivity. Typical metallization are either in copper or in aluminum, okay? And then these other materials are also used, but they're a lot less common. So you can see why we switched to copper, because copper has lower resistivity. And as we will see, the intrinsic delay of the wire depends essentially on this resistivity. So if you want a wire that has lower delay, okay, then you will use a lower resistivity material, hence copper. Okay. I think also we will see that not only there is the introduction of copper that is important, but we also increase the number of interconnect layers, and that is to make routing easier, okay? To give more degrees of freedom, and you make wires shorter. We'll talk about this in a little bit. These things will become a little clearer, okay? Now, so metal is a big contributor to routing, okay? But sometimes we also want to route things in poly, and this is particularly done, for example, if you look at the standard cell level, like if you look at the flip-flop layout, a lot of the local routing is either done using diffusion layers or silicides. This is because typically if you look at the layout of a digital library, the standard cells will try to use only one layer of metallization, so say metal 1, okay? And so, if you have to cross, you need a layer that is not metal 1, but typically you don't want to use metal 2. So you will end up using either polysilicon or diffusion, okay? So any idea why? So if you just use polysilicon, okay, you will get pretty crappy conductivity. So what people do is deposit this silicide, which is either tungsten, silicon, or titanium, and that lowers the resistivity. Okay. However, what you need to remember is that both the resistivity of the diffusion as well as the resistivity of the silicide are much worse than the resistivity of the metal. Okay. And this is why you don't want to route signals very far using polysilicon. I mean, at the gate, at the level of a cell, okay, you're talking about distances that are of the order of a few microns, maybe 5 or 10 microns if it's a flip-flop. Okay, and so your routing distance is maybe a small fraction of that, a couple of microns, 5 microns. So that's okay, right? But if you want to route 100 microns, you won't ever do it with the silicide or with the diffusion. Unless you really don't have a choice, okay? So this is a table that I think is more useful to remember than the previous one with resistivity, which is the sheet resistance. So, okay, this is what I was saying, right? Look, this is typical aluminum sheet resistance for metallization in metal 1 will be like 0.1 to 0.15 ohms per square. Okay, and for a higher metal layer, it will be maybe like 50 milliohm per square. Anyone knows why it changes? I mean, they're all aluminum, right? So why, if you take a top metal layer, a bottom metal layer, and a top metal layer, I can tell you this, that the sheet resistance is different. Any idea why it will be different? Yes? Right, the thickness is different. Very good. All right, so the thickness will be different, okay? And so also these numbers are for aluminum. For copper, they might be a little bit lower, but typically copper is used in newer processes where the metal is also thinner. So in the end, there may be around 50 million, but they're definitely not. They're not much better than this. Okay, and so you can see that even if you take N plus poly with the silicide, which is what will be a gate, okay, the resistance per square is about 40 times larger. Okay, so this means for the same resistance, you can route about 40 times less far using poly than you can route using aluminum. Okay, diffusion is also the same level, N plus P plus poly, and then light diffusion is low. So keep in mind that both this layer and this layer, if you are doing analog design, you will use to make resistors. So whereas typically a wire you don't use to make resistors because you need a wire that is very long to make a decent resistor, like 1 kilo ohm, right? So this gives you the idea that these layers are actually, not very good conductors. Okay. Also, can anyone say what could be another disadvantage of using diffusion for routing compared to, let's say, metal? Let's say that they, and I will tell you that it's not the resistance, because we're already talking about resistance. So what do you think could be one difference between using diffusion to route and, for example, metal 2 in aluminum? Yes?
Maybe the capacitance of the diffusion kind of depends a little bit with the voltage you apply.
Okay, so linear capacitance for the diffusion, that's right. But there is even, so this is true and it's a good answer, but there is even a simpler answer that has to do with what I was saying before. So diffusion will be So let's try to draw the cross section. This will be diffusion, okay? This will be P sub, which is grounded. Then you have SiO2. Okay, and then let's say that we even have metal 1, okay? So, you know, the diffusion is closer to ground than to the substrate than the wire, okay? So per unit area, it has more capacitance. Does this make sense to everyone? And, okay, so if you take metal 1, if you take metal 3, it will be, you know, even farther away. So if nothing else, you wouldn't want to use diffusion because of the capacitance. Okay. So now let's look at how we will model the interconnect. So I think that to first order, this is a good model. So you have a wire, all right, and then connected to some driver that is a logic gate, and then you know, you will model it as a resistor due to the logic gate, and then the capacitance due to the wire. Okay, so now let's say that this wire. So let's try to understand when is this a good model. Okay. So what are we ignoring in this model? Yes. Okay, we are ignoring the output capacitance of the driver. That's true. We are also ignoring load capacitance. It's another thing that we are ignoring. In other words, there is nothing connected here, whereas probably there will be something. But I think that we are also ignoring something else, right? That we spent. So what else are we ignoring? And then I want someone else to answer. Right, resistance of the wire. So now we are modeling the wire just as a capacitor, okay? So when do you think that this is a good? Now we'll go in a lot of detail, in a lot more detail at least about this model and how we improve it. But first, let's try to think about when this is a good approximation. Okay? So we have said that we are ignoring the capacitance of the driver. Okay, we are ignoring the load capacitance, but you know, these are easy to include, right? Because we just add them in parallel, and okay, they change this capacitance. If this wire is big, this capacitance will be larger. Okay, so it will only change by a little bit. In any case, you know, you just add them and you're done. Instead of having R driver C lamp, you have R driver C lamp plus C load. Okay, so then the next question, the next thing that we are ignoring is the resistance of the wire. And so let's just try to think about. So you know, you will think that when is the resistance of the wire negligible? When would you think that? Just based on your intuition, really. Yes? When it's short, but I think we can be more quantitative. Okay, so let's do another example. So there is already a resistor here. It's the resistor of the driver, right? So one thing that could be reasonable is to say, well, if the resistance of the wire is 100 of the resistance of the driver, right? Then it will change the delay by 1%. Fine. We don't really need to worry about it, okay? Because probably anyway, the uncertainty and the delay of the resistance of the wire is larger. The driver is larger than 1% anyway. So how about we say that the resistance of the wire needs to be some fraction of the resistance of the driver for this model to be accurate. Okay? That seems reasonable, right? So the next question is, what's the resistance of the driver then? what's an order of magnitude for the resistance of a transistor? Someone from this side? Or this side is not the very back?
Order of magnitude of capacitance? So yeah.
No, what's the order of magnitude of resistance of the drive? You know, if you take a transistor and you, for example, tie the gate to VDD and tie the drain to VDD, right? That will be, and the source is a ground, and this is an NMOS, or you do the opposite, the PMOS, all right? Then this would be the resistance of the driver when it's pulling down, right? Because it's, or actually, to make it more similar to resistor, you can think that the drain is low enough that it's in triode or whatever. Then how much it will this resistance be? But I mean, I'm not, you know, I don't want to know like 1.563 k ohm. I want to know, is it a kilo ohm? Is it 100 ohms? Is it 10 ohms? Is it mega ohm? Is it, yes? 10 ohms, yeah. So actually, 10 ohms will be a very big transistor. I think the one thing that you can remember as order of magnitude is that the VDD is about 1.2 or 1 volt, right? And then the current that the transistor puts out is of the order of 1 to a few milliamp per micron, okay? So let's say that this transistor is, for example, even if it's a 1 micron wide transistor, okay, over L min, which is a pretty wide transistor, because L min in the modern process would be like 65, right? 65 nanometers, okay? So this number will come out. So you can say that VDD over ID is as units of resistance, and it's some measure of what this resistor is, okay? It's not what it will be, but so this for a 1 micron device will be about 1 kilo, okay? For a minimum size device will be about 10 kilo, let's say 90 nanometer, if you make it 1/10 of a micron. So this driver resistance is actually 1 to 10 K, okay? I'm sure someone knew this, but so the idea is really that whenever the wire resistance is less than, say, 100 ohms, okay, it doesn't do too much damage to leave it out. So the next question is, how can we make the wire resistance 100 ohms? Let's say we use poly. Yes? Right, so you just use the table from before. I think poly, we said it was like 4 salicylated poly, right? It was about 4 ohm per square. So to make it 100 ohms, you need 25 square. If you are in 65, this means that, and the poly is minimum width, this means 1.5 micron, okay? So after 1.5, yeah, that's right. After 1.5 microns of routing length, you've already picked up all this resistance, 100 ohms of resistance. So that's, that's pretty significant. That's why you don't make these connections longer, right? And then if you're using aluminum, okay, where we have, say, 0.1 ohm per square, you need 1,000 squares to get to 100 ohms, right? And therefore, you need a length of maybe 100 nanometer times 1,000, which would be 100 micron. Okay, so 100 micron is pretty long. So you're talking that, for example, if you have gates, right, you will have So for metal, right, we're talking about 100 microns. So 100 microns, a gate will be, again, of the order of like 10 microns by 4 microns. This will be the area of one typical flip-flop, for example, okay? And so you need to go across 10 gates for the wire delay to start being, for the wire resistance to start being significant, okay? So this just to have an idea based on, if you're just routing, presumably from like this gate to the next, okay? Then the resistance will not make too much difference because you're going only like 10 microns or so. So unless you route in polysilicon, then it'll be okay. Okay? So now let's say that we do want to add this resistance, okay? So the next question is, how do we add the resistance? So let's go back one slide to this. Okay, now I want to add the resistance of the wire to this model, okay? Now, as long as there is only capacitance, there is only one node in this model, right? This output node. And so, you just put the capacitance here. Now, when you put the resistance, okay, where do we put the resistance? If you think about it, the capacitance you pick up length by length, right? Every increment of the wire adds a little bit of capacitance, okay? So as long as the resistance is 0, these capacitors are all in parallel, okay? But when you make the wire resistive, every little bit of wire, okay, not only adds capacitance, it also adds resistance. Okay, so in other words, if I have this long wire here, okay, this is like seen from the top, okay, then every section will add C and R, okay? So let's say that the total resistance of this wire is R, okay, or in other words, this wire is as a length L, okay, and as, it has a resistance per unit length which we indicate with small r times L, okay, just like here. And then it has a total capacitance C, which is equal to small c times L, okay? So it turns out that you can write a differential equation for this RC line, okay, because you can write the current flowing into each incremental length of capacitor, and then the voltage related to the voltage difference across the resistor, right? Just using KCL essentially. And you get this equation, okay, that tells you this is essentially a heat transfer equation, a diffusion equation, okay, because it's the second derivative in space and first derivative in time. And you get this delay, tau. Tau is L squared over 2 RC. So it turns out that if you solve this differential equation, okay, the delay of the wire is not R times C, okay? So if you take all the resistance of the wire, okay, and you draw it like this is the R wire. Then you take all the capacitance of the wire and you put it here, Cy, okay? This will be a reasonable model of the wire. Do you want me to go on this other side? Can everyone see? Like you can think of, putting all the resistor of the wire in one place and all the capacitance of the wire at the end, right? So then what's the delay if you apply a step here? What's the delay here at the output? It will be 0.69 R wire, C wire, right? Okay, that assumes in a way that to charge this capacitor, okay, the current needs to flow through this whole resistor. But this is not really what happens. What happens is that to charge the first part of this capacitor, the current needs to flow only through this small resistor here, right? And then, to charge this, it needs to flow through this resistor and this resistor. and so on. And so only the last capacitor sees the total resistance. Only the last bit of capacitor sees the total resistance. And every capacitor along the way sees a smaller resistance. Okay? And so I think that you should have covered Elmore delay. Is that right? Or, well, anyway, so if you make an approximation, so one way to find the delay is to sum the value of each capacitor, okay, times the resistance that it sees from the source to that capacitor, okay, looking left. So this guy sees R wire. This guy sees R wire, times L minus delta L. So each of these capacitors, you go from right to left, sees a little bit less resistance, okay? So the net result is that the delay is not the full RC, but it's actually half of that, okay?
So I have a quick question.
Yes.
Normally when we have a time constant, we just have it in terms of RC, and now we have like a length dimension squared in there.
Yeah, you can think about it as R times L is R. So this R and C are R per unit, resistance per unit area. So the units of R is ohm divided by meters, okay? And the units of C, small c, are farads divided by meter, okay? And so you can think that R picks up an L and becomes a resistance, okay? And C picks up an L and becomes a capacitance, okay? From being length normalized quantities. So now, so if there was not these two, probably no one will show this slide, because all they will tell you is that, the wire just behaves as a resistor equal to the total resistance in series with the capacitor, with the capacitor equal to the total capacitance, okay? So it wouldn't be there would be no interesting effect. The interesting effect is that because of the distributed nature of the capacitance, okay, and the resistance, the effective RC product that you see is half of what it would be if you took all the resistance and all the capacitance and you just put them as lumped elements. Does this make sense? Yes?
For getting that tau, do you just do the integral of the Elmore delay?
Yeah. So this is the equation, okay? Because, there is two things here. One thing is because this is a distributed network, okay? We are trying to approximate it with one time constant, okay? So we are taking essentially a system that has infinite poles, and we are approximating it with the system that has one pole, okay? And so it goes between going from this equation and this tau, okay? Because we solve this exactly, and we get this equation, okay? But this equation is very hard to implement, for example, in a simulator. Okay, so what you do is you say, well, what I'll do is I'll just replace this network with some equivalent RC. How should I choose that RC? I will choose it so that I get the same propagation delay for a digital signal, okay? So now then the RC that you choose is actually this value.
No, I'm saying, do you arrive at that value?
Oh, this you arrive through Elmore delay, yes.
Okay.
Yes, and you arrive through Elmore delay.
It's just like R times L.
Yeah, so this guy is R times L. You will do an integral over in Elmore delay. I think a simpler way to do it, if you don't want to do an integral, is just to break it into n pieces. Each is L over n. Okay, and I think we're going to actually do this right away. Yeah, okay. So if you model the wire with n segments, and each of them is long L over n, okay, and then you calculate the Elmore delay, okay, then what you get is the following. So you will get that, let's say that I modeled it with the small n, because I'm lazy, I don't like drawing. So this will be C over n, C over n, C over n, C C over n, and this will be R over n, R over n, and R over n, R over n, where R is equal to small r times L, and C is equal to small c times L. Okay? So if you do this, then to do Elmore delay, start from this capacitor. Okay, this guy gets C over n times all of R, right? So in other words, we can also write this as C over n times R over n, okay? And then this will be times n, okay? Then this guy here sees, n minus 1, right? Because to the left we only have 9 units now. Then this guy here will see n minus 2, and this guy here will see 1, okay? So now, you all know Newton's sum of the first n integers, that is n times n plus 1 over 2, okay? The reason is that you pair these integers, right? You start with, you take the first and the last. The first is 1, the last is n, and the sum of them is n plus 1, okay? Then you take the second and the last two, the one before the last. So this will be this plus 2, and it gives you n plus 1 again. Because you are choosing pairs, there's only n over 2 pairs. Okay, each gives you n plus 1. So this gives you, so this becomes C over n times R over n times n plus 1 over 2. And you get RC times n plus 1 over 2n, okay? And then because n, okay, this is a finite approximation of an infinite length, so what you will do in reality is you will choose n larger and larger. The larger you choose n, the more accurate this becomes, okay? And so as you let n go to infinity, essentially this just becomes 1/2, right? This 1 becomes negligible. Okay, and this is what you get, the RC over 2. And so essentially, okay, this just summarizes, but I think bottom line is that you're pretty safe. If you look at all these values, it's really only 50%. If you look at the time, the equivalent time constant, the 63% rise time means that the error is 1 over e. Okay? But in general, you can argue that the delay is always about half of what it will be if you took all the resistance and you put it with all the of the network that has the total resistance and the total capacitance as an RC network. Okay? Because I mean, here you're looking at 2.2. 10 to 90%, okay, the lumped delay is 2.2 and the distributed delay is 0.9. I mean, you can call this 2 and this 1. I mean, it's probably okay. Okay, so now let's say that you have this long wire in your SPICE simulation and you want to include it in your SPICE simulation, okay? How would you do that? There is 2 ways. Okay, one way is that actually some simulators or tools have a wire model, okay, that is distributed, and internally the simulator does some approximation to this differential equation, okay, and you just need to say what's the resistance per unit length and what's the capacitance per unit length and what's the length. So you don't need to think very much, okay. So that actually is often available. If it's not available, then what can you do? You can just make your own approximation to the distributed nature, okay? And so how do you do it? You just put some RC network, okay? And essentially what you do is you model the, you need to put some R's and some C's. Okay, so you split the wire into a bunch of sections. For each section, you either put a pi network like this. This is called pi because it looks like the Greek letter pi. Okay, or you put this T network. Okay. The difference between these two, is small. In this case, you break the capacitance in 2 pieces, and you put just 1 resistor. In this case, you put 2 resistors and 1 capacitor. Notice that they're all symmetric, okay? This you should try to do always, because the wire, if you flip it 180 degrees, it doesn't know that, this should be symmetric. So these networks are all symmetric from left to right. So this will model a wire that goes from here to here, right? So presumably, as you use more Rs and Cs, you make, as you use more sections, essentially, of this network, you go from here to here. Your simulation gets more accurate, okay, but it also gets slower, and you also have to do more work, okay? So typically, the principle with these things is that you want to use the simplest possible thing that is accurate enough, okay? So, I mean, obviously, you can always use the most complicated possible thing, and you will always get the right result. But maybe your simulation takes 3 times as long as it needs to, okay? So typically, you should try to figure out which one of these is the best, and is good enough. I think honestly, for most things, probably something like a second-order network will be okay. Okay, I think you will. Only if you want it to be really accurate, you will go for something like this. And what changes, okay, in this as you go to higher order, and I think it's in the next, well, actually it's in a later slide, but it's that. So when this network behaves as a first order RC, and this network becomes, as in this case, a third order RC, and so. Okay, there are 2 parameters, right, that you care about. This is the step that you put at this side, okay? And then you are observing the output on the other side. Okay, so for a first order network, the output will be a single exponential, okay, RC. For a second order network, there will be 2 exponentials, okay, because there are 2 poles, 2 capacitors, 2 poles, right? And as you go to higher networks, essentially this shape becomes less and less like an exponential. It becomes more like a slow ramp, okay? And I guess this is not fair. So the crossing point, I guess, as you go to higher order, maybe remains the same, because all these networks have the same 50% to 50% delay. Okay, so the instant at which the output crosses the threshold will be the same. But the shape will change, okay? And it will actually become less and less steep as you go to higher order, okay? And for example, this could be important. I don't know if you guys talked about short circuit power, but if you have a slow rising waveform, then you have more short circuit power than if you have a fast rising waveform, okay? And so for some things, this actually is important. But I would think that most often you wouldn't need to use anything bigger than this. Most often, actually, you will just use this. But this is probably okay for most cases. Okay, so now let's go back to the initial model. This is where we started, right? Is that we have our driver essentially right here, and the wire, and we want to know what's the delay. Okay, so you can do Elmore delay again, and find that the delay is the total wire capacitance times the source resistance plus the delay of the wire. Okay, or in other words, it behaves as if the wire capacitance, so a resistance that is the driver resistance plus half of its own distributed resistance. So we already kind of saw that, okay? And if you want to be more accurate in the 50% time, you use this 0.38 instead of 0.69 over 2. Okay, it's a small change. Okay, so this is what I was talking about. That the diffusion, the signal propagates along the line, not as an exponential. Okay. It's not a single exponential, the signal at the output, because each section of the line gives you one exponential, okay? Does this make sense? And so as you go from left to right, as I was saying, not only there is a delay, but also the signal becomes slower and slower in the delay, right? So in other words, I can tell you that the delay is 10 nanoseconds, okay? And the input is a step. After, if I told you only these 2 things, you can't drive the waveform. You cannot draw the waveform at the output, okay? Because you don't know what shape the waveform has. To first order, we always approximate it as a step. So we will say that the output is another, perfectly steep transition 10 nanoseconds later. Okay? But in practice, it could be something that looks like this, that is very steep. Okay? But it could also be something that rises very slowly. Okay? And for the wire, it's more like the second thing. It's like this. Okay? If it's a long wire. Yes?
What is X?
X is the position along the wire. So you're like, imagine that you have this long wire, right? It's a long trace on a PCB, or it's like a long piece of metal on your chip, okay? And then you take an oscilloscope probe and you like probe different points, okay? And let's say the oscilloscope is magic and it doesn't load the measurement and all that. Then if you start very close to the source, okay? Then the behavior of the wire will be more or less like a single exponential, okay? But as you go further and further along the wire, it will behave more and more as the signal you will see more and more this like slow rise time, okay? And this rise time doesn't have to do, you will never get a signal that looks like this at the output of a single RC network, okay? Because you will always get a signal that looks like this, but maybe is, translated in time. This is just a slow rise because of the distributed nature, okay? Okay, now we're gonna switch gears because so now we're gonna be looking at this equation that doesn't model exactly what we were talking about before, but models a slightly different thing. And the slightly different thing is a driver driving a wire, but now there is a so we've got a driver, okay? This driver has actually absolutely no capacitance. It drives a wire, okay? And then it drives some output capacitance C out, okay? So now the question is, I want to make this network as fast as possible. I want to minimize the delay between the time I apply the step and the time I measure the output, and the time the output crosses 50%. Okay, what can I do? Well, let's say this driver is magic, so it doesn't add any. You can make it as wide as you want. The capacitance is always 0. Clearly, this is not true, but okay. So what will you do? Yes. Yeah, but okay, you can do Elmore delay and calculate what the delay will be, right? And I think you get that formula, okay? But intuitively, what you want to do is you want to minimize the delay, okay? You will make this driver as wide as possible. That would be one thing that would be reasonable, okay? Or you will replace this driver with the appropriate exponential horn and all that, okay? And make this driver delay go away, okay? You are still, the wire will still have its own delay, okay? Which is this part plus this part, okay? So now, if you look carefully, this part here especially, and also this part, once you fixed the resistivity of the layer, the sheet resistance of the layer, okay? And you fixed the distance that you're going, okay? This number you can make smaller by making the wire wider, okay? Because you are reducing R wire and keeping a C out constant, okay? So let's look at each of these terms. This number you reduce by making the wire wider, okay? Because you reduce RW, C out is fixed, okay? This number are DC wire as well as RDC out. You can reduce by making the driver bigger, okay? But this number, you can't reduce, okay? Why? Because if you double the wire width, okay? You halve the resistance, okay? But you double the capacitance to first order. So in other words, this product is dependent only on the technology, okay? Which in particularly on two things: the thickness of the wire, okay? And the material, the resistivity, which is the material, okay? And the distance. Finished. I mean, it doesn't. You can't do anything about it. All right. So this means that if you think about it in these terms, chips get bigger and bigger as we scale, right? If you take a microprocessor from like 2000, okay, and you take a microprocessor from today, the chip is much larger today than it was, okay? In addition to that, the logic delay is much smaller today than it was 10 years ago, okay? However, the metallization was aluminum 10 years ago, and now it's copper, which is 2 times faster. That's it, finished, okay? And this term, you can presumably the length has increased of the interconnects, right? So this term has gotten bigger, and the logic delay has gotten smaller. So in other words, the importance of the wires compared to the logic delay gets larger and larger over time. Okay? Does this make sense? And so now we are really in a regime where when you want to communicate from one side of the chip to the other, this must be very carefully planned. Okay? And okay, so there's a few things that you can do that in part I've this is pretty interesting because copper is the only essentially low-hanging fruit in this space. Copper, we know how to deposit, so we do it. Okay, it's like pretty much the lowest resistivity material that we can cheaply get. Okay, what can you do? You want to reduce this product, okay? And essentially, you can only do it for real by reducing the resistivity. So you can do it. There's two things that you can do. There are both material. One is change the wire resistivity, okay? The other is change the dielectric, okay? Because the dielectric will change CW, right? Every time you change the dielectric, there is always, you calculate the capacitance, there is always an epsilon of the capacitance. And so people are doing both things. But the dielectric that we are using right now, they're around 3 of dielectric constant, between 2 and 3. There hasn't been a large improvement over that. Okay, they're not silicon dioxide. Okay, silicon dioxide will be 4. But the resistance we are fixed with copper. Okay. So we need to deal with this at the circuit level. Okay, so in the future there might be other things coming up, like for example optical superconducting. I don't know, but optical communications could happen eventually. I mean, there's certainly a lot of people working on it. But so right now what we can do is a few things. One thing that we can do is use big wires. This helps with this part, but not with the other. Okay. The second thing we can do is we can be smart about where we put things, okay? So, typically if you have 2 blocks that always talk to each other, you don't put them on 2 opposite sides of the chip, right? You will put them closer. The third thing that we can do is insert repeaters. And actually, okay, we can do a few things. One is insert repeaters. Sometimes what you can do is if you have a wire, for example, in a memory that is in polysilicon, you can use a bypass with a better wire that is in metal, okay? This doesn't solve the problem that if you have a wire that is in metal, there's nothing better, okay? So, but this is valid, right? So let's say that you want to drive this polysilicon word line. You can short it with the metal. You can also drive it from both sides, and this will reduce. You know why driving from both sides will reduce the delay? Yes?
Perhaps the resistance
and halves the capacitance, right? So okay. So let's look at this. This is not too clear. If you drive this line from this side only, okay, the signal starts from here, starts propagating, and the last point that the signal will propagate to is this, okay? So now we don't have this driver, okay? And so the length is the full length, okay? The length of the propagation. And the delay, as we know, is L squared, okay? Now, if we drive the signal from both sides, the signal starts at the same time from here and here, and propagates towards the center, okay? So each half of the signal travels only half the distance, which means that the delay is actually 1/4. Okay? So, so when you have a situation where you have a long line that is in polysilicon, for example, or in diffusion in any low resistivity layer, then you probably want to do this. Okay? So when can this happen, first of all? It can happen if you have an area where you can't use metal. Okay? This can happen. If you can use metal, then you can just strap the, you can route metal on top of the polysilicon and then put contacts. And essentially, you know, the signal will propagate only in the top layer, and then it will just go down, right? Because it doesn't want to go through the high resistivity part. But this assumes that you can actually use metal in the same place as poly. If you can't, then the other thing is the only thing you can do. Anyway, so going back to the previous thing of using repeaters. So now we have a different problem, okay? What we are going to ask ourselves is that we have this long wire, and we are unhappy with the delay of the wire. It's too long for whatever reason, for what we want, okay? And so we're going to try to make the delay smaller by breaking this wire into pieces, okay? In this case, we are breaking it into m pieces, and after each piece, we introduce an inverter. Okay? And so what's the idea here? The idea is that, let's say the inverter has no delay. Okay? I mean, why does this work? Let's say that the inverter has 0 delay to understand why this works. Okay? Now, each of these pieces has a delay that is proportional to the square of its length. Okay? So if the inverter has 0 delay, the total delay growing from left to right will be just m times the delay of one section. Okay? Does this make sense? Now, because I made the section 1/mth of the length, okay, the delay of the section is actually 1/m squared of what it was before. And so overall, the delay is only 1/mth of before. Does this make sense? Because, okay, I have a length L, okay? And so the delay is proportional to L squared, okay? Now, I break L into m times L/m, okay? And notice that I add the delay of these pieces, okay? And so what I end up is that I get m times L/m squared. Is this clear to everyone? This is like step 0. So from this, okay, then you get the total delay is actually is L squared over m, okay? Or in other words, it's m times smaller than in this case, okay? Do you guys see it from here? Okay. So what did I neglect to do in this? So this explains why this can work, okay? Because the growth of the delay with length is quadratic, okay? Therefore, the delay and delays for the same length, it's better to split it into smaller things, okay? But this, okay, so then this will tell you that, you know, to make the delay as small as possible, you just choose m equal to infinity, right? So you put an infinite number of buffers, okay? So this doesn't work because the buffer doesn't have 0 delay. It has a finite delay. Correct? So, I mean, I made this derivation. I told you. The buffers have 0 delay. Let's neglect the buffer delay. And, you know, we just, these buffers are magic. The signal comes here and comes out with 0 delay, but they isolate the impedance from left to right. Okay? Then what you get is that not only it's better to put buffers, but if you could, you would put an infinite number of buffers. Okay? And the key is that the buffer breaks this chain of R's and C's, okay? Now, because the buffer behaves as a voltage source with the new resistance, right? So when you look at, for example, a piece of capacitance from this part, okay, you accumulate the resistance of the wire all the way to this point. Then you accumulate the resistance of the buffer, and then you're done. You are at VDD or ground, okay? Whereas if you were driving it only from this side, you would like keep going, okay? So, okay, so clearly, okay, so if the buffer delay is 0, the optimal number of buffers is infinity, okay? Impractical and not true. Because the buffer delay is non-zero, there is actually an optimum number of buffers. So, okay, if you model the buffer delay as usually let's say that the driver has some resistance RD, okay, and then has some input capacitance CD, okay, and then you are also not only you have the freedom to choose how many buffers there are, but also how wide each of these buffers is, okay? You can choose a fan out of 1 inverter, fan out of 2, fan out of 4, you know, you name it, okay? And so the resistance of the buffer will be RD over S, and its capacitance will be CD times S. Okay? So you can write then the delay of one section with this buffer present is equal to this. And okay, this might look a little daunting, but actually it's not that bad because this part, okay, is the intrinsic delay of the wire when the length of the wire is 1/mth of the total length, right? You can see that the unit length, the R per unit length, C per unit length, and then the reduced length, okay? And this constant is, you know, 0.7 divided by 2 takes into account the distributed effect, okay? Then this part is, if you did Elmore delay, will be the capacitance at the input of the inverter times the resistance of the wire, okay? The capacitance at the input of the inverter is C times CD, because CD is the capacitance of a unit size inverter, and S is the scale factor, okay? Sorry, it's S times CD. And this is the resistance of the wire, the resistance per unit length times the length, okay? And then this part out here is the resistance of this inverter, okay, times the driving resistance of the previous inverter, plus the resistance of the wire times the resistance of the driving inverter, okay, plus the self-loading of the inverter. I mean, if you don't get it, you can just go back and solve it. You just do Elmore delay. You know, the only thing that you need to remember, and then there is M of this, okay? So now look at what happens. As you increase M, okay, as you increase the number of buffers, essentially, you make each individual line shorter, okay? And therefore, you make this thing between the parentheses smaller, okay? Because inside the parentheses, everything decreases as you increase m, okay? But you increase this multiplying factor, okay? So what happens? Let's say we start at m equal to 1, and we increase m for some fixed scaling factor s, okay? Initially, what happens is that this term, if this term dominated, this term decreases very quickly because it's m squared, okay? And it decreases faster than this part increases, okay? So the delay starts to go down, okay? But then, if you think about it, if you make this 0, increasing m, this part, this m and this m get multiplied out and it becomes constant. And this part, this m and this m get multiplied out and becomes constant. And these two terms actually increase, okay? So if you plot the delay as a function of m, it will look like this, okay? There'll be a minimum, in other words. Okay, and this minimum depends on s, on how big the driver is, okay? And in fact, the larger the driver is, I think the smaller this m is, but I think you should verify it. This is just my gut feeling. Okay, now, someone took the trouble of, okay, so what would you do? You take the derivative, okay, you can do it. I haven't done it in like 10 years, but because someone took the trouble of doing it for me, but you should do it once to make sure that you get the same result. There might be a typo, and if no one ever checks, then this gets propagated for like 20 years. I think this is correct. You can take a derivative with respect to m and to s and minimize, and you find this expression, okay? So this essentially tells you what's the optimum number of repeaters, okay? And look at this. The optimum number of the repeaters depends on the ratio of the propagation delay of the wire when there is no buffer, okay? Divided by the delay of the inverter, okay? When it's loaded with a fan out of 1. And so if you take the inverter delay to 0, the optimal number of repeaters becomes infinity, as we said in the beginning. Okay? And then the optimum S is given by this ratio. So you can use an even more sophisticated model. Actually, okay, so I think then the interesting thing is what you get is that after you do this optimization, essentially you are balancing out the delay of the wire with the delay of the inverter, okay? So in other words, you are creating a wire that is about as good as the inverter. Why is this? Because let's say your wire has a very high RC product, okay? Let's say it's polysilicon, for example. Then, you can put a lot of inverters before their delay becomes comparable to the delay of the polysilicon, okay? Or in other words, think about it in these terms. After you do this optimization, essentially, the delay of the inverter and the delay of the wire are about the same, okay? This is really what's happening. And so if this wire is very slow, it's a high RC layer, then this wire will be short, okay? Which means that for a total length, there will be many, many sections, many, many inverters, okay? If this wire is fast, then this segment will be long, okay? And then there will be fewer inverters. But the bottom line is that the delay of these wires, okay, after you do this optimization will be independent of what wire you started with, okay? Because what you are changing is you are changing the length, okay? To make it similar to the delay on it, to make it, let's say, the same as the delay of an inverter. This is really the big picture, okay? So, I mean, this is pretty remarkable. It's just math. You do the math, this comes out. Okay. So now, the next thing, which we have like 10 minutes to go over, is decoders. So why are decoders married to wires? Because decoders occur in a memory. Memories are these parts of the chip where you, for example, have cache, L1 cache, L2 cache, so on, that have a lot of transistors, and you need to read out this data. Okay, so then there's very long wires. Okay, so that's why these two things are. We talked about it in the same lecture. Okay, so first of all, we want to build this cache. Okay, and I don't know how much cache these laptops have today, but it's typically very big. If you look at the layout, the area of the chip is largely cache. Okay, there's more cache than logic. So let's say that it's 1 million unit cells. Okay. Then what are we gonna do? Of course, we could lay out these unit cells as a row, and have a memory that looks like this thing. Now, people like chips to be squared. Okay, so if you start to have a lot of things that look long and skinny and they're like a meter long, that typically probably your chip will not end up being square. So you don't do that. Instead, you try to make something that is square, which means that instead of organizing this 1 million cell in one row, you organize them into square root, some number of rows and some number of columns. And I don't know, if I was me, I would choose the number of columns and the number of rows equal, right? But you can make sometimes you can make twice as many rows as many columns. But in general, the number of rows and the number of columns will be the same. Okay, so that it comes out with a nice square layout. Okay. Then what I'm going to do is I'm going to provide the memory an address. So I'm going to say I want to write, so there is 1 million cells, right? And I'll say I want to write a 1, for example, in the cell number 384,000, okay? So now I need some logic that what it does is it takes this 384,000, which is some binary number, okay? And converts it into what's the row corresponding to 384, it selects this row, and then it selects this column, okay? And this cell is exactly the 384,000. So first I need to figure out some scheme. For example, let's say I have 1 million cells. Let's say I have 2 to the 20 cells, okay? I can split them into 2 to the 10 rows times 2 to the 10 columns, okay? Then I can choose each row and each column with a 10-bit word, okay? So I need some piece of logic that, what does it do? It takes as an input, okay, the log 2 of the number of cells, of rows, okay? So let's stick to this example. We have 2 to the 20 cells, okay? There's 2 to the 10, which is 10,024 rows, and 2 to the 10 columns, okay? Then I want a piece of logic, okay, this decoder. What it does is you put in 10 bits. There is one decoder for the rows and one decoder for the columns, okay? Because as I said, the way it works is that, these two decoders operate independently. I send a 20-bit word, okay? Because to choose between 2 to the 20 cells, you need only 20 bits, right? You take these 20 bits, you split it into 2, 10 go to the row decoder, and they select one row, okay? But of course, they select all the cells in this row. And then you take the other 10 bits and you send it to the other decoder, and it selects one column. So it selects all the cells in this column. So what you're left with is just the one cell that is in the intersection of this row and this column, okay? Pretty straightforward. So now, so you have n bits coming in, okay? But you have 2 to the n wires coming out, okay? Because each row and each column, they're one wire. imagine for each row and each column there is a transistor that you need to turn on the gate if you want to select that row. Okay? This is pretty much what it is. Are you guys following? Okay. So now how do we do this decoder? This is actually very simple. A decoder is just like this. Okay. Let's say I have these 2 to the 10 wires, okay? And I number them 0 to 10,023, okay? Then, each of these numbers has a binary representation, okay? So this guy will be 0, 0, 0, 0, 0, 0, 10 zeros, and this guy will be 10 ones, okay? So for this guy, I can say that I want this wire to be high, okay, when all the inputs are 0. So whatever is connected here is given by A0, A1, A0 bar, A1 bar, A2 bar, blah, 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 A9 bar. Okay? Now, for this guy, what I'm going to connect it to is A0, A1, blah, 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 A9. So these are all negated, these are all non-negated, okay? So now, what about line 15? Who is going to volunteer and tell me what's line 15 connected to? I mean, what's the logic that drives line 15? So first of all, what's the binary representation of 15 with the 10 bits? I mean, I chose one that I think is doable. Huh? So it's 4 ones from left to right. Let's say that the LSB is on the left and the MSB is on the right. So it'd be 1, 1, 1, 1, 0, 0, 0, and then 3 more zeros, 0, 0, zeros. Okay? So what logic? Okay. So then what's the logic function that you're going to use here? You can kind of look from here and here. You should be able to find the pattern. Correct. A0, A1, A2, A3, and then A4 bar, blah, 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 A9 bar. Okay? And so on and so forth. Okay? Now, I think we just I just showed you this organization, like square. This guy selects a row, this guy selects a column, and then you read out just the intersection, okay? Okay, and this is same thing. Okay, I guess one thing that is so these are all AND functions. If you have an AND, you can use De Morgan or put an inverter. Okay. So now I think the interesting part is the following. We have this decoder. Okay. It has all these outputs. Okay, and it needs to perform essentially this complex AND, right? Because if you have, as we said, the 10-bit address, it's a 10-input AND. Okay, and if we have a 20-bit address, then it becomes a 20-input AND. Okay. So the question is really how we implement this function using the obtaining the minimum delay. Okay, because in the end, when your computer pulls things out of cache, you want it to happen as quickly as possible. It's not that you want to wait around. Okay, so there is an example for 256 by 256, and I guess I'll just leave it for next time, where so Jan will cover this. But you can imagine that there is two main things. I'll just leave it at this. I won't go through the details, okay? But I'll tell you kind of how it works. It works as follows. You have this 8 input gate, okay? What are the things that you need to worry about to optimize the gate? You can implement this input gate in any way you want. One way, of course, is you make a complex gate with like 1 million transistors in a stack. And another way is that you make many gates, each of which has 2 or 3 inputs, okay? So, so of course, as you make smaller gates, you get more stages. You make a bigger gate, fewer stages, right? So the question is really, what's the optimal number of stages? So there's 2 things. One is the path effort. So you need to calculate the path effort, okay? And then we know that once we know the path effort, the optimal number of stages is essentially log of the path effort, okay? And the optimal effort per stage is just about E meaning the Nepère number, okay? So what represents the path effort for this decoder? 2 things, okay? Number 1, the load, okay? The load of the decoder will just be given by, okay, the decoder, let's go back to this, and I'll show you quickly. Okay, what does represent the load? The decoder drives this whole row, okay, from this side, and from this side this drives this whole column, okay? So if you have a 10-bit decoder, it means that there are 2 to the 10 rows, okay, and let's say there are also 2 to the 10 columns, okay? Then the load will be the capacitance of a unit cell, okay, times 2 to the 10, times the number of columns, okay, which we said is 2 to the 10. In this example, it's 2 to the 8. Okay, 2 to the 8. All right? Then there is the branching effort. Why is there a lot of branching effort in this decoder? So think about it this way, okay? How many of these AND gates there are? Okay, it says it on the slide. 2 to the n. Why are there 2 to the n gates? I mean, there are 2 to the n wires, right? Each gate has one output, then there's 2 to the n gates. Okay. Now, if you think about it, imagine that you focus your attention on one of the, so we said the 2 to the n gates and there are n inputs, 8 inputs, okay? Now I want to ask you, each of these inputs, to how many gates is it connected? All of them. Okay, another opinion? You said half? Who's for all and who's for half? Like, raise your hand for each input goes to all the gates. No, so no one thinks that it goes to all the gates. Okay, who thinks that it goes to half the gates? You can't abstain. Like, you need to pick a side. Pick a side. I mean, look. I'm not even the regular lecturer, so what do you care if you say the wrong thing? Okay, who's for half? I'm for half. Anyone else for half? Okay, so you two. So everyone else, I assume, is for they go to all. Okay, so no, they don't go to all. Why? Because this is like a very simple problem. Okay, if you think about it, you're gonna cover all these 2 to the n with all the so this matching is 1-to-1, right? The number of different values, okay, that you can give to these inputs is exactly 2 to the n, right? If I give you 8 bits and I tell you how many different 8-bit numbers you can give me, how many are those? 2 to the 8, okay? So each bit can either be 1 or 0, okay? And therefore, there will be exactly half of these addresses that will have, for each bit, okay, half of these will have this bit equal to 1, half of these to the n values will have it equal to 1, and half of them will have it equal to 0. Okay? Like as when you write, let's say we write all the 3-bit numbers, right? There will be 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0. Then you get 1, 0, 0, and you repeat this, right? So exactly half of these, come with the 1, half come with the 0, half come with the 1 here, half come with the 0, half come with the 1 here. Okay? So therefore, for each input wire, half of the cells receive the input, negated, okay? And half receive it non-negated. So if you, so the branching effort is actually 2 to the n over 2. Okay, because each input goes to half as me. And so from that, you can find the total path effort, and then you can calculate the number of stages. So you can already imagine that this path effort is pretty large, right? Because it's there is a 2 to the 10, and then another 2 to the 9, essentially. So, so you end up with actually a pretty large number of stages. But anyway, that's it for me. Remember the midterm. Also, I think there is one more thing about